it is done. Let's illustrate this discussion with a simple problem. So let's consider a case where m equal to 3 and n equal to 2. That means there are 3 number of origins and there are 2 number of destinations. And the quantities at the origins are specified as 45, 60 and 35. And the quantities which are demanded are given as 50 plus and 60. So as you can see here, if you add up the total supply or the quantity which is available, it comes out to be 140, whereas the quantity demanded is coming as 110. So this problem is of unbalanced type, so we have to add a dummy destination and attach the surplus quantity of 30 to this particular destination, and then this problem becomes a balanced problem which can be handled with the standard techniques. So the cost data is given for all transportations. For the dummy destination, the costs involved are 0 and the quantity attributed to the dummy destination is 30. And the linear programming form of this transportation problem would be to minimize the total cost. So 3 times x11, that is 3 is the cost of transporting product from first origin to first destination. So this is the cost of transporting x11 quantity from origin 1 to destination 1. Similarly, the other costs can be added and the total cost is the one which needs to be minimized. The constraints are given in terms of the quantities which are supplied from origin 1. So this is the origin 1 which has got total quantity of 45 available with it, and it is supplying, the first origin is supplying to first station, second station, third station. The quantities as shown here, x111, x12 and x13. So total dispatch from origin 1 to the different destinations must be equal to 45. Similarly, for the second station it is 60 and the third station it is 35. The second level of constraints is looking from the destination side. The quantity demanded by the second station is 50. So this 50 quantity is getting supplied in terms of x11 quantity from first station, x21 quantity from second station and x31 quantity from the third station. So all these quantities, they add together to the 50. Similarly, for the second station it is the 5th equation and the third station it is the 6th equation, and all quantities are positive or 0. So that is how you formulate a transportation problem in linear programming form. Now this particular problem can be solved using the methods what we have learned in the linear programming class, and it can be handled. Note that although the equations are in standard form, they are not in the canonical form, in the sense we don't have any pivot quantities. For example, if you look at x11, the quantities along this column are not 0 everywhere. So you have this particular non-zero number which does not qualify x11 as a pivot. Similarly, you will find that none of the variables are pivoted. So this is not in the canonical form. So you have to first bring it to canonical form and then solve the linear programming problem. So that involves a lot of computation, and there are better techniques which are specially evolved for transportation problem which are used. For solving the transportation problem, we use a specific table format which is known as a Transportation Tableau. This is a table on which all operations of transportation problem are done. So this particular table is of size m by n, where m is the number of origins. The origins are specified on different rows of this table, and the destinations are specified on the different columns of this table. So there are m number of rows and there are n number of columns. The last column indicates the quantities which are available at different origins, and the last row indicates the different demands those are required by the different destinations. At every intersection point, so for example, if you take second row, second column, this indicates the quantity inside this particular cell. X22 is the quantity which is supplied from second origin to second destination. In the next cell, it is quantity which is from second origin to third destination. The quantity which is specified in the square block inside the cell is the cost of transportation for transporting, in this case, from second origin to second destination, or here it is from second origin to third destination. In this way, this entire table is created, and the various cells are manipulated in a specific approach in order to solve the transportation problem. Let's illustrate this tableau for the problem that we have just seen. So the problem what we have seen has 3 number of origins, and after addition of the dummy sink, it has got 3 number of destinations. So we are having 3 number of rows corresponding to 3 origins, and there are 3 number of columns corresponding to 3 destinations. Note that the last destination is a dummy or a sink. Now let's put the values in this table. The last row, the last column will have the quantities which are available at different origins. So first origin it is 45, second origin it is 60, and the third origin it is 35. Similarly, the quantities which are available at the first destination, the demand from the first destination is 50, demand from second destination is 60, and the demand from the dummy destination is 30. Now we have to put the costs. So cost C11, C12 are given here. So C11 is 3, C12, that is from first origin to second destination, so that is 2, and C13 is 0. So since this is a dummy destination, it will have the cost of transportation as 0. So similarly, for C21 it is 1, C22 it is 5, and for dummy it is 0, and C31 is 5, C32 is 4, and for dummy it is 0. So in this way, the initial tableau is prepared. Solving the transportation problem involves finding out how to determine the quantities which are to be supplied from every destination from every origin to different destinations. So we have to determine these particular numbers. The first step in solving a transportation problem is to obtain an initial basic feasible solution. The basic feasible solution has got number of basic variables equal to m plus n plus 1. So for our problem, which has got 3 origins and 3 destinations, we will have this initial number of basic variables as 5, and all remaining non-basic variables are 0. So out of total 9 number of variables which are there in this particular problem, there will be 5 will be non-zero, and remaining will be 0. In order to obtain this initial basic solution, which will seed the further solution, there are different techniques available. Some of them are northwest corner method, least cost method, and Vogel's method. All these three methods are described in the accompanied handout which are supplied with this session. In this course, we are not going into details of how to perform this, how to solve the transportation problem in detail. Those of you who are interested in going in more details can go through the handouts to understand the details. The figure here shows the initial solution obtained by northwest corner method. So we can verify here that there are 1, 2, 3, 4, 5 number of basic variables, and the solution for the transportation problem is initiated with these numbers. The next step is to find the optimal solution with the least cost. For obtaining the optimal solution, again there are different methods. Some of the methods which are described in the handout are the stepping stone method and the UV method. As a final solution to the present problem is given by the different quantities which are shown here, and the minimal cost is 200 as compared to the initial cost which was 435. So this concludes our discussion about the transportation problem. Let's have a look at the next case, which is known as the assignment problem.